Hi again, this is the third in a series of 5 videos on row reduction, and in this video we are going to talk about what it means for a matrix to be reduced. A reduced matrix is also known as a reduced row echelon matrix, and it's a matrix that meets 4 separate conditions. I've gone ahead and given each of these conditions an informal name just to help us remember and talk about them. But before we talk about each condition in detail, I just want to mention that some sources might list a different number of conditions. For example, they might combine 2 of them, but that's okay. Their definition is going to be equivalent to ours. The first condition we are going to call the leading one condition. And it says that moving from left to right, which there's nothing special about, that's just the direction in which we read text, for example. The first entry in each row that is not 0, so in other words that's non-zero, is a 1. And these entries are called leading ones. Let's see how this looks in an example. We'll just go row by row in this first matrix. In the first row, the first entry we encounter that's not 0 is actually just the first entry. And is it a 1? It is. So that row checks out. How about the second row? We have 0, 0, and then the first entry that's not 0 is a 1, so that's good. Next row, 0, 0, 0, and then the first entry that's not 0 is 1, so that's okay. What about this last row? This is a little bit different. I glossed over this when I was giving the description because it's best encountered in an example. Let's see what the description says about this, though. It says that the first non-zero entry, if there is one, has to be 1. If there's no non-zero entry, that's okay. So this row is all right, and the whole matrix does satisfy the leading one condition. Next matrix. First row, the first entry that's not 0 is here, and in the second row, it's here, and they're both 1s. So this matrix is okay. And what about the third matrix? Our leading non-zero entries are here, here, and here. But this third entry, it's a negative 1, which is bad. We don't want negative 1. Okay, so just remember it has to be a positive 1. And the matrix in part C then does not satisfy the leading one condition. Next condition we are going to call the staircase condition, and it says that each leading one is to the right of any leading one in a higher row. Let's see how that looks in an example. So our leading ones in the first matrix are in these circled positions. What type of staircase might this make? Well, you can see that the first step is a steep vertical drop, and that's not good. So in other words, the first, or rather the second leading one is not to the right of the leading one above it. So this matrix does not satisfy the staircase condition. What about the next matrix? Leading ones are here and here, and the staircase looks like this. Again, we have an elongated step, but this time it's okay. Let's go back and look at the description and see what it says about this type of staircase. It says each leading one has to be to the right, but not necessarily immediately to the right. In other words, our second leading one, it's 2 columns over, but that's okay, as long as it's somewhere to the right. And the last matrix, our leading ones are in the positions I've circled, and this won't work because the third leading one is not to the right of the leading one above it. Next condition. We are calling this the clear column condition, and it says that each entry above and below a leading one has to be 0. Let's take a look at some examples. In the first matrix, our leading ones are here and here, and if you notice, above this leading one we have a 2, which is bad. It should be 0. So this matrix does not satisfy the leading one condition. The matrix in part B is very similar. The leading ones are actually in the same locations they were before. And again we have a 2 above a 1. But that's okay because it's not above a leading one. So the entries above and below the leading ones, so in the first column with the first leading one, the only other entry is 0. And in the second column with the second leading one, the only other entry in that column is 0. So this matrix is okay. Alright, and you may have noticed, if you did, otherwise I wouldn't concern yourself with this, but you may have noticed that the staircase condition, it actually guarantees that all the entries below a leading one have to be 0. So I didn't have to specify that separately up here, but just for emphasis, all the entries both above and below a leading one have to be 0. Last condition we are going to call the 0 row condition, and it just says that if there are any 0 rows, which are rows consisting entirely of zeros, then they have to be at the bottom. Let's take a look at some examples. In this first matrix, we have 2 0 rows, and they're both at the bottom, so this matrix is okay. It's alright if you have more than one, as long as more than one 0 row, as long as they're all at the bottom. In the next matrix, again we have 2 0 rows, but this time we have a non-zero row that's below a 0 row. That we don't want. So the 2 0 rows, in other words, they're not both together at the bottom. So this matrix does not satisfy the 0 row condition. And the last matrix, this one's pretty simple. We just have one row with all zeros, and the main thing we're interested in is that it's at the bottom, which it is. So that's okay. Okay, let's take a quick quiz and try to figure out if we can decide whether each matrix is reduced. So in this first matrix, we will just check each condition one by one. Let's see if you can remember the 4 conditions. They were the leading one condition, the staircase condition, the clear column condition, and the 0 row condition. How about the leading one condition? Well, our leading ones are in these circle positions. So all the leading non-zero entries are 1. That's okay. Our staircase looks all right. And each column with the leading one, the first column, In this first column, all of the other entries besides the 1 are 0. It's the same in the second column. We have all zeros except for the leading 1, and the same thing in the third column. So that is okay. And what about this last condition, the 0 row condition? We haven't seen an example like this yet, but where there aren't any 0 rows, but that's okay. It's just that if there are any, they have to be at the bottom. So that checks out as well, and you might be surprised, but this matrix actually is reduced. Even though this matrix has a 2 in it, and that 2 is even above a 1, but that's okay because it's not a leading one. And some people also think that all the entries along the diagonal here have to be 1. That's also not necessary. Let's take a look at the second matrix. Again, we'll just check each of the 4 conditions. The first condition is the leading 1 condition. So in the first row, our leading non-zero entry is here, and in the second row, it's here, and in the third row, it's here. And these entries are all 1. That's what we want. That condition's okay. The next condition is the staircase condition, and we have a nice staircase, so that's okay. And the next is the clear column condition. Remember, we're just checking the columns that have a leading 1. So the first column does contain a leading 1, and all the entries besides that leading 1 are 0. That's what we want. How about the second column? Well, in this case, we have a 2 above the leading 1, and that's not good. We want that to be a 0. So this matrix does not satisfy the clear column condition, and therefore it's not reduced. Okay, and again, we said it does satisfy the leading 1 and staircase conditions, but not the clear column condition. How about the 0 row condition? Well, we talked about that a moment ago. What happens if there are not any 0 rows? That's okay. It's just that if there are any, they have to be at the bottom. So that condition's okay, but because it's not the case that all 4 conditions are satisfied, the matrix is not reduced. Alright, and then the last matrix, we have our leading 1s, our staircase, our columns. Each column with the leading 1 is clear. That would be this column. The only other entries besides the leading 1 are 0. Same in this column and in this last column. And the last condition to check is the 0 row condition. And then we said a moment ago, if there are no 0 rows, then that's fine. So this matrix is reduced. Alright, that's it for this video. I just want to mention before we wrap this up that after the next video, in which we will actually solve our first system of equations, we will learn an easier way to decide if a matrix is reduced. But it was important that we talked about the definition of a reduced matrix first, because that way, when we start our row reduction in the next video, we'll understand clearly what the goal is. Thanks for watching, and I'll see you in the next video when we solve our first system.